The physical world does not deal in absolute boundaries. Temperature, speed, and pressure shift along a continuous gradient, lacking exact cutoff points. But classical computing evaluates information using Boolean logic, a crisp logic system. In this model, every proposition must be evaluated strictly as either true or false. When a crisp set maps data, an element's membership is restricted to two binary integers, a 0 for total exclusion or a 1 for total inclusion. This mapping forces a hard, arbitrary threshold onto data that is naturally smooth and continuous. These binary thresholds struggle to manage complex engineering systems in real time. A sensor reading in a chemical plant doesn't instantly snap from safe to critical at the exact crossing of a decimal point. It moves through a transition. To model physical reality accurately, we cannot force continuous variables into crisp binary boxes. Instead, the mathematics must account for the transitions between those boxes. Fuzzy logic is the mathematical methodology designed to handle these transitions, which the theory refers to as lexically imprecise propositions. This diagram shows the shift. In a fuzzy set, membership is not binary. An element is mapped to a continuous membership grade, represented by any real number between 0 and 1. This fractional mapping allows an element to exist partially within a set, moving away from the binary requirement of full inclusion or total exclusion. Despite the name, this process is not an approximation. A fuzzy logic system is time invariant, mathematically rigorous, and entirely deterministic. This high-level architecture shows how the system functions. Physical data enters as a crisp input, is evaluated through a fuzzy rule base, and is finally translated back into a crisp output for the hardware to execute. By utilizing fractional membership, a fuzzy logic system handles control problems where traditional mathematical models are either non-existent or too computationally demanding for real-time processing. To construct these models, we plot the universe of discourse along the x-axis. This axis represents the complete range of all possible physical values applicable to the chosen variable. The y-axis represents the membership grade, denoted by the Greek letter mu. This measures the exact degree of truth for the data point within a specific set. Looking at graph B, a crisp interval graphs as a rigid step function. Moving a point along the x-axis jumps instantly from 0 to 1. In graph C, vertical walls are replaced by a continuous slope, creating a triangular fuzzy number that connects them gradually. Tracing a single data point up that slope shows how the membership grade smoothly tracks a fractional value as the input variable changes. This continuous slope alters the logic of system evaluation, allowing a single variable to possess fractional membership in multiple overlapping categories at the same time. Every fuzzy set is defined by its specific membership function. To make these functions programmable, we divide their geometry into measurable zones. This chart details that anatomy. The flat top region of the trapezoid is the core, where the membership value is exactly 1. Any data point landing in the core represents an element that is completely part of that set. The sloped outer edges make up the boundary region. This captures elements experiencing non-zero but incomplete membership. The absolute base of the structure is the support region, including the entire domain where elements have any non-zero membership grade. Zaday's notation provides the mathematical syntax to map these anatomical zones to linguistic labels, like young or fastest. This geometry allows the system to translate subjective human assessments into programmable, deterministic data. Once data is mapped into these fuzzy sets, the system must process it. We need a way to mathematically evaluate logic conditions, even when data points overlap. We do this by extending classical logic gates, like and or, into continuous set-theoretic operations. Fuzzy OR, the union operation, traces the highest outer perimeter by taking the maximum membership value. And, the intersection, traces the shared inner geometry using the minimum value. Not, the complement, subtracts membership from 1, mapping the inverse negative space. By redefining rigid Boolean operators as continuous max and min functions, a system can compute complex rules across highly ambiguous data streams. These continuous set-theoretic operations are exactly what allow us to move from pure mathematical theory into applied, real-world engineering. Looking at the architecture again, the process begins at the fuzzifier, mapping precise physical inputs to assign a fractional grade. Those enter the inference engine to process overlapping grades simultaneously. Finally, defuzzification translates this back into a single crisp number to trigger an action. Fuzzy logic serves as a deterministic framework that enables machines to compute with the continuous nuance found in real-world physical systems.